Hi, I'm Jerry, and today I'll be teaching Dijkstra's. In this video, I'll be going over the intuition about how Dijkstra works, and if I have time, I'll also go over the implementation and data structure used to run Dijkstra's. So what is Dijkstra's? Dijkstra's is a graph traversal algorithm, like BFS and DFS that we've seen in class so far. However, it has one additional property. In addition to traversing the graph, we're also going to find the shortest distance and path to each node in the graph from some start node. Let's see what we have here. On the left-hand side, we have the graph we're going to traverse and some start node S. On the right-hand side, we have a list of labels that corresponds to each node in the graph that we're going to use to keep track of the shortest distance to each one of those nodes. So let's start by filling in the initial values for each node. A really good way to visualize Dijkstra's is to imagine yourself as a very nearsighted person that can only see one edge away from where you're standing. So where is it that we're standing in the beginning? We start at the start node, so that's where we're standing. And what we're seeing at that point is something along the lines of this here. Okay, so we're starting at the start node S, and we look around, and we're very nearsighted, so we can only see the nodes A and B that we can get to by taking this edge of distance 2 and this edge of distance 3 respectively. So we have this list of nodes here of all the nodes that we know exists in the graph, but right now we can only see that there exists a path from S to A and S to B of distance 2 and distance 3 respectively. So how will we update the information in our list? What's the distance to S? The distance to S is 0 because we know there exists a path to S, namely the one by just standing still, and that has no cost. To get to A and B, we know there exists a path to A and B of distance 2 and distance 3 respectively by taking these edges. What about the last two nodes in the graph? We know they exist in the graph somewhere, but we don't know if there exists a path to them. So what we're going to do is, okay, let's get rid of this highlighting here, and we're going to label S with a distance of 0 because we know we can get there by staying still. We know we can get to A. At the very least, there could be a shorter path, but we know we can get there at least by taking the path from S to A of distance 2. And the same goes for B with a distance of 3. For C and D, if you remember the picture, we don't know if there exists a path to them. So what we're going to do is label them with a distance of infinity, noting that there may or may not exist a path to them, but we cannot know for sure as of right now. So what do we do now? First, we're going to mark S as visited. Note that we have not visited A or B yet. We only observed A and B standing at S. So you can imagine visiting a node as having physically stood there. We don't have to look at visited nodes ever again. Hopefully that makes intuitive sense. If I had time, I would prove why we can make that assumption. So now what do? We're going to choose a new node to visit. And the node we're going to choose is the one that we haven't visited yet with the shortest distance so far. So of the remaining unvisited nodes A, B, C, and D, the one with the shortest distance so far is A with a distance of 2. So we're now going to move to A. So we're going to do that same update procedure that we did at S. We're going to look around. Remember, you're this really nearsighted person that can only see one edge away from you. So we're going to look around and see is there any new nodes that we can update with new information now that we're standing at A. The only node we can see at A is S because it's the only one with one edge away from us. Unfortunately, S has already been visited, so we ignore it, and there's no other nodes that we can update. So we're going to just mark A as visited, having done nothing at A, unfortunately. Okay, we're going to use that same idea and visit the next unvisited node with the shortest distance so far. So between the unvisited nodes B, C, and D, the one with the shortest distance so far is B with a distance of 3. So we're going to move on now to B. And we're going to perform that same update procedure. We're going to look around and see 3 nodes, S, C, and D. Once again, S has already been visited, so we don't ignore it. However, something interesting happens over here. Nodes C and D, we once didn't know if there exists a path to them, but now we know there does exist a path. And namely, that path is the path from S to B of distance 3 that we know already exists. And now we can take the path from B to C of distance 5 and B to D of distance 2. So now we're going to update our list with our newfound information. We now know we can get to C with a distance of 8. That's 3 plus 5. We also know we can get to D with a distance of 5. That's 3 plus 2. We're also going to mark B as visited, as we have done before, because we have physically stood there. And we're also going to move on to the next unvisited node with the shortest distance so far. So of the remaining unvisited nodes, C and D, the one with the shortest distance so far would be D with a distance of 5. So now we're going to perform that same update procedure. We look around at D and notice that the only unvisited node that we see from D is C. We already know there exists a path from S to C, the path from S to B and B to C of a total distance of 8. However, we now know that there exists a new path from S to C, namely the path from S to D and D to C of a total distance of 7, 5 plus 2. We notice that this new path has a better distance than our old path because 7 is less than 8, so we're going to update C with this new value of 7. Noting that the next time we want to visit C, we would rather take this new path from S to D and D to C than our older one. So once again, we're going to mark D as visited now because there's nothing left to do here, and move on to our final unvisited node left in our graph. So now we're going to perform our final update procedure. We look around C and see is there any unvisited node that we can update. The answer is no, so we just mark it as visited. Now that all nodes have been visited, our algorithm is finished. Our right-hand side now contains the short distance from S to every node in the graph. Because I'm out of time, I'm going to end the video here. Thank you for watching, and I hope you have a great break. Thank you.